All right, let's dive in. Today, we're basically going to be detectives. We're on a mission to uncover exactly how a neural network learns, and it all comes down to calculating one single, super important value, the gradient.
I mean, really think about it for a second. When a neural network gets something wrong, how does it fix itself? It's got all these little knobs and dials inside, weights and biases, sometimes millions of them. How does it know precisely which ones to turn and by how much to do better next time?
Well, that's where this thing called the gradient comes in. The gradient is the treasure map. It's the exact set of instructions that tells the network, hey, turn that dial a little to the left and that one a tiny bit to the right. Cracking how this map is made is our entire mission today.
So, here's our game plan. First, we'll lay out the mission. Then, we're going to find the master formula that holds all the secrets. From there, it's all about solving 3 key clues, one by one. And once we've got them all, we'll put them together to crack the case.
Okay, trying to look at the whole network at once, that's a recipe for a headache. So we're not going to do that. Instead, let's zoom way in, put our magnifying glass on just one single connection, one weight, and see how the magic happens there.
This is our target. Now I know, that notation looks a little scary, but all it's really asking is a super simple question. If I just barely nudge this one little weight, how much does it mess with the network's total error? That's it. That's the number we're after.
To find that number, we need a blueprint. And in the world of calculus, that's the chain rule. We need it because changing a weight doesn't cause a direct hit on the final error. Nope, it's a domino effect. The weight changes the input changes the output, and that finally changes the error.
And boom, here it is. This formula shows that domino effect perfectly. This is our master formula. It looks like a lot, I know, but trust me. Just think of it as a puzzle with 3 pieces. 3 clues we have to solve.
Okay, first up, let's grab this first piece of the puzzle. This clue is all about figuring out how much the total error changes when the final signal or the activation from our node changes. Let's isolate this part and figure it out.
Next, we're on to the second clue, this middle part right here. This one connects the node's output to its input. It asks, if the information coming in changes a little, how much does the information going out change? It's all about the node's internal logic. And our final clue brings it all home. This last piece connects everything back to the actual weight we're trying to figure out. It asks a simple question. How much does the node's input change when we fiddle with this specific weight? Solve this, and we've got all our puzzle pieces.
All right, the investigation is officially on. Let's solve clue number 1. What's the relationship between this node's final output and the whole network's error?
So how does this work? Well, the total loss is really just the sum of all the little squared mistakes from the output nodes. The cool part is, when we take the derivative for just one of those outputs, a sub 1, all the other parts of the sum that don't have an a sub 1 in them, poof, they just go to 0. We're left with one simple little piece, and a quick use of the power rule gives us our answer.
And there it is. Clue number 1 is solved. The answer is just 2 times the difference between what the node actually spit out, a sub 1, and what we wanted it to spit out, y sub 1. It's basically just a measure of that node's personal error. 1 down, 2 to go.
Okay, moving right along to our second clue. This time we're digging into how a node's output signal reacts when we change its input.
You know, this one's actually the easiest of the bunch. The output of a node, its activation A, is, by definition, just what you get when you push its input Z through some activation function G. So, the derivative of A with respect to Z is, you guessed it, just the derivative of that function G prime. Simple as that.
And just like that, clue 2 is in the bag. The answer is g prime of z sub 1, the derivative of whatever activation function we decided to use. See? We're flying through this.
All right, time for the last piece of the puzzle. This is the one that connects everything back to the weight we actually care about adjusting. Let's do this. So remember, the input to our node, z sub 1, is what's called a weighted sum. That just means we take the signal from each node in the previous layer, multiply it by its connection weight, and add all of those up. So when we take the derivative with respect to just our one specific weight, w sub 1, 2, everything else in that big sum just vanishes. The only thing left standing is its partner, the activation from the node it's coming from, a sub 2. And boom, clue number 3 is solved. The answer is just a sub 2. And with that, we have everything. All the clues are on the table. The case is pretty much closed. We did the hard detective work. We've tracked down and solved all 3 clues. Now for the really fun part. Let's put all the pieces together and see what we've found.
Okay, watch this. We start with our master formula blueprint. Now, let's slot in the answer for clue number 1. Perfect. Now let's plug in what we found for clue number 2. Looking good. And finally, the last piece, clue number 3. And there it is.
So this is it. This is the gradient for that one single weight. And if you look, you can literally see our 3 clues sitting right there. You've got the node's error, multiplied by the derivative of the activation function, multiplied by the signal from the input node. This is the magic number the network needs to get just a little bit smarter.
Now, of course, we just did all that work for one tiny weight. So what does the whole network do? It runs this exact same calculation for every single weight inside it. Then it does that for every single piece of training data, and it averages all those results together to get the final game plan.
So we did it. We cracked the code and we figured out how the gradient is calculated. But that kind of leaves one big question hanging in the air, doesn't it? We see how the math works, but why on earth is this whole famous process called backpropagation? What's going backwards? Well, that's an investigation for another time. Thanks for joining me.